Okay, hi everyone, and welcome to the fifth TIA Centre seminar of the academic year. So today I'm absolutely delighted to introduce Professor Jin Tae Kwak. So Jin Tae received his PhD in computer science from the University of Illinois in 2012. He earned his Master's of Science degree in electrical and computer engineering from Purdue University in the USA in 2007. And in 2012, he joined Centre for Interventional Oncology, Clinical Centre, National Institute of Health, USA, as a research fellow. He served as a tenure-track faculty member in the Department of Computer Science and Engineering at Sejong University from March 2016 to August 2020. And he joined the School of Electrical Engineering at Korea University in September 2020. And his research interests include multimodal medical imaging, digital and computational pathology, and large-scale and efficient AI systems for medicine. And the title of today's talk is Pathology Knowledge-Guided AI Models in Computational Pathology. And Jin Tae, we're really delighted to have you join us in person. So with that, I'll pass over to you.
Hello, everyone. Thanks for the warm introduction. I'm Jin Tae Kwak from Korea University. Basically, I'd like to share our recent works, basically using the large-scale AI models and the multimodal MLLMs on computational pathology. So we are particularly interested in using the knowledge that we have on pathology and combine it with the AI models. Diagnosis and various tests in pathology. So I think most of you already know how the field evolves. So basically, there's a lot of development and transformations in the field, from the introduction of digital scanners, image processing, machine learning, deep learning techniques, and these days, mostly driven by the large-scale models and the foundation models. So in the past, pathology look at the tissue slide under the microscope, and they make decisions and predict grade labels, and also they provide the pathology portion to look like these. And what we have done in the early days was basically try to develop an algorithm to extract useful features, image features most of the time. But then ever since the era of deep learning, it is basically driven by the data, the tons of the images, and using the CNNs and transformers. But still, we need a lot of the label data, but ever since the foundation models come out, then we're able to use both the labeled and unlabeled data. And nowadays, you see lots of the foundation models, particularly in pathology, released every month or the quarter. And there's a lot of things available. And these studies basically shows that they can outperform all the models that we have developed for the last few decades. Then that's kind of how the field evolved, and very beautiful history about it. But then I think we can look at these in a slightly different manners. If I go back to the conventional pathology, there was basically the knowledge transfer between the humans, right? Especially during the medical training and the mentorship. So there was basically the medical doctors and the students. There was a human-to-human knowledge transfer. But if you just say make comparison to the early computational pathology era, there was still the human-to-human knowledge transfer between the pathologists to the engineers, like myself. But this is primarily it's driven by the human-to-model knowledge transfer. So from the engineers to the machines. So mostly working on the feature extraction part. But nowadays, it is more tuned to the machines and the models. So there's two types of knowledge transfer from human to model. So engineers to the large-scale models in the form of the architectures and the training strategies and so on. There's another part as the data to model knowledge transfer. So we just pour lots of the data, not just the images, but with the other modalities of the data. And then given these two types of knowledge, they get bigger and bigger and smarter. So some of you are already familiar with, and people with already talked about the collaboration between the clinicians, like pathologists, with these AI systems. But what our lab has been focused on over the past couple of years, then these are we already have these good large scale models, and how we utilize them. These are strong enough, as we say, this is foundation models. So what we have first done was to test whether how strong these models are. We tested under two different scenarios. Not going to details, but some of you already know that the foundation models, they perform differently across different tasks and data sets, and also the adaptation methods matters. So for example, you can see here like linear probing, full fine-tuning, partial fine-tuning, and the parameter efficient fine-tuning. There are many different types of adaptation techniques. Depending on which one you choose, the model may perform differently. And which model you choose, and which foundation model you choose, they may perform differently. And also for the few-shot or zero-shot learning scenarios, they perform very bad. Because in most of the cases, they perform like under 50%. So there's still a lot of rooms to improve. I think this is a huge problem because in pathology, there are a lot of tasks and data sets we need to handle. So it's not like that we already have one model that can handle everything, because there's still there's a lot of rooms to improve. And when we work on this specific task, there are different approaches. In the past, we basically build the task-specific models. So basically have one model for each task. But in the foundation model era, so basically share one big model. And then mostly we have like these small, like, for example, for classification tasks, we have classification hat for each. So which means that we have randomly initialize the classification hat that needs to be trained for every single task. Randomly initialize means that we have no prior knowledge. For foundation models, we do have the prior knowledge. So we have a strong prior knowledge, but still we have a small part, but we have no knowledge on that. But then we think there's a way to get around this. So we propose the task agnostic generative models, which is basically combining image encoders, so there's the image foundation model, and the text decoders, so the language models together. So you can have the image encoder that is pre-trained on the pathology images, and also the language decoder that is pre-trained on pathology data or the natural language data. And then by fine-tuning these models, you can adapt your model to any tasks in pathology. So the outcome of this is like, given this one single image, then the model will generate the class labels as a natural language form, not like a one label as the conventional classification model does. But we realized that framework cannot learn multiple tasks efficiently, because if you just train multiple tasks at the same time, they cannot handle these data sets very efficiently. You can just the knowledge basically can collapse among different tasks. So to address this problem, we propose this framework we call it a CAMP. So where we have the pre-trained visual encoder and the text decoder. We call it as a common knowledge of the pathology they have. And we have the adapters, independent of adapters for each task. So we call this as a task-specific knowledge they can learn from each task. So when we actually handle each task, so we just combine this pre-trained visual encoder and text encoder with the task-specific adapters to handle each specific task. So by using this framework, we have shown that we're able to improve the performance of the pre-existing foundation models across different tasks. But shortly after, we realized that the framework can handle many different tasks, but there's no way we can utilize the task-specific knowledge to another task because we learn the adapters independently. So let's say we have learned 10 different downstream tasks, but we learned those task-specific knowledge, but there's no way we can use them to handle another newly coming task. So that leads us to develop another framework, which is the continual learning framework. So here we use the expert quantitative model. I think many of you are already familiar with. So it is kind of similar. We have like experts, which is basically the trainable weight for each downstream task. But the difference between this expert quantization model from the adapters that we have proposed previously is that the final decision basically is just a combination of different experts. Okay? So as we trained more and more on the downstream tasks, then we will basically have more knowledge to handle new tasks. So we did experiments using 7 different data sets, as you can see in this screen. So we did like 2 experiments. So one is starting from chameleon all the way to TCGA CSV, and the other experiment is just doing opposite way. So forward and backward experiments. So the second experiment starting from TCGA CSV and all the way back to the chameleon. Okay? And so the one on the right side is this our result. You can see that our result is recorded as the co-scorer performs on average better than the competing models. More importantly, we see that their performance is different in forward and backward scenarios. For example, the BRCA, the third row in the first table, we got like 93.7% accuracy. But in the backward scenario, we got like 90.766%. So there's a like 3% difference. In other data set of tasks, it's the same. So we had just that the previous knowledge that we obtained from the downstream tasks matters. Okay, so depending on which task you have learned previously, that affects to handle the new task that you have. So we just that it's not just about the matter of whether we can use the prior knowledge or not. It is just a matter of how we optimize those task-specific knowledge that we have previously. That's we will try to handle at the moment. And this is an ongoing work on our side, which is the multi-level analysis for gastric diagnosis. It's not just for gastric, for other diseases the same. It's the diagnosis is not just at one level. And for gastric diagnosis, we can group in many different ways, but one way we can put this as at the course level, we can classify it into 4 different groups, like benign tumor, cancer, dysplasia, and inflammatory disease. And each of them can be subdivided into 5 grade categories. Depending on process, you can even have 3 different levels. But in these cases, how can we handle it efficiently? So if you think about the conventional ways, you may just have this one model that just classify them with like 10 or 20 different labels, or you have 2 different classifiers, one for course level, one for fine level, and so on. But our goal was to have one model, which is basically the similar framework, which combining the imaging encoder and the text decoders, but then it can handle multi-level diagnosis problem. So the way we put this is that so we frame this as a series of questions and the answers, and each of these questions are related to each other. For example, in the first question that we have for this particular input whole slide image is like, is the slide positive or negative for H. pylori? H. pylori is important for gastric diagnosis. And then the second question is saying that determine the category of diagnosis represented in this H. pylori positive slide. So we use previous answer that we had and to as part of the second question, and then the answer should be dependent on our answer of the first question. And the third question, if you see that, then it says like this H. pylori positive slide shows malignant features. So, for example, our answer on the second question was saying this is a cancer slide. So, using those information together, then we try to basically, the third question is about the subtype of the cancers. So we framed in this manner and compared it against a variety of the MRI approaches and BLM approaches and then foundation model approaches. It shows that we outperformed these existing models across 4 different data sets. Some of them are private and some of them are public data sets. So far what I have shown you is basically the classification models, where we come up with a image encoder and text decoder model for classification models. But mostly people using the same kind of models for report generation, not for the classification part. But you have already seen, I'm sure that you have already seen similar works, right? Given the whole chart image, and they are looking at multimodal LLM to generate the reports like you can see on the right side. But then we found that the way we process this is not optimal because we mostly adopt the MIF framework. MIF is just dividing the whole slide into a number of patches, like maybe more than 10,000 patches, and then you just summarize them to generate one representative features, maybe like multiple features, but then use that features to generate like these long sentence. It should be restricted by the information bottleneck. So with that, we were trying to address this problem, and then we try to mimic how the pathologists examine these slides. So the way the MIF process is that they just look at the one slide, it's a whole slide, it's a one gigantic image. Okay? But when the pathologists look at this, examine this tissue slide, they do not treat it as a one slide, one big picture. So if you give the slide to them, then they may pinpoint some of the important regions and then go to zoom in and look around the surrounding areas. And then they maybe move to another regions and also examine deeply, right? So if you imagine this, the field of view they have as, so it just becomes this stream of images, not just a one static image. So to us, it's just more like a video, not a one static image. So we try to have a model that can process the whole slide images in that manner. So we call this as a video reasoning in pathology. So ideally, we like to have a stream of images as the pathologists go over the slide, but we don't have the data set yet. So what we did was to use the educational video in the YouTube. If you go to the YouTube, there are many educational video. So we process them. So in the educational video, the pathologists just go over the slide and explain what they are seeing in the slide. So we just say download those data set and just a lot of post processing to make a short video clips and then get rid of all the unnecessary information. And then using that data set, we built a model that we call as video lava model. So that's basically just the VLM model that expands the stream of images instead of just a one single image. So the result has looked like this. So it's given a stream of images. If we ask some questions like what is the best diagnosis for this slide, then the model will process the stream of images and give us the descriptions for that. Okay? And it can also give the final diagnosis on it. And we wanted to examine our model on different data sets, but there is no video data set. So what we were able to do is just use some existing data set that are similar to our problem. So we just benchmark on the text generation and also the V3A data sets. As you can see in this slide, we were able to improve the performance compared to the computer models. And this is the example of the inference that our model made. So the video itself is generated by the pathologist. So this is an educational video. But this text script is just generated by our model. So as the person just go through the slide and it just show you explains what you are seeing on the screen. Okay. And yes. So it's just at the end, we're just saying like overall, this one has some indicative of the high grade carcinoma and so on. Okay. So we talk about basically our work on related to the multimodal LLMs. Right? So it's by combining the image encoder and the text decoders. But we have realized that what we have done is basically brought the foundation models and did some fixes and modifications, sometimes add some additional components and try to adapt to the downstream testers. But why we do so? Because we believe that the foundation models does have some knowledge. We call it as AI-driven knowledge. So if you believe that is a really true knowledge that we can utilize, then can we use it more actively? Not just as a pre-existing models, but can we just use their knowledge for the downstream test that we have? So this is the very first work that we did, a very simple experiment. What we did here is that we just employed the VLM model with the vision encoder and text encoder. And given one input image, what we have done is that we prepare the word pool, basically the keyword pools that we believe this is relevant to the data set or the images that we try to analyze. And using this VLM, we matches this input image with the pathology keywords, okay, and find the most relevant keywords, and then use their text embeddings to generate the representative text embedding vectors. So we call it as a text-based image embedding. Then we did the experiment with 4 different text pools with different levels. And then we did the clustering on given 4 different data sets. So the first row is a visual, which means that using just the image features directly from the visual encoder. And the next 4 rows is basically using the text-based embeddings. As you can see that they give us better clustering. Okay, so again, these embeddings are basically coming from the matches text keywords. Each keyword has their own embeddings. So we just summarize all of those and use them for the cluster. So this tells us that we are able to use those text embeddings matches to the input image. Maybe we can use it for image classification. So here we generate the text embedding in the same manner, but we combine it with the image features. Then we did the classification on, I think this is on the gastric data set. On gastric grading, we were able to improve the performance quite substantially. And we were also able to provide the relevant keywords because naturally it comes with the text embeddings that are matches to each of those input images. So it's not just the class label it can provide, but also provide the relevant keywords so that the pathologist or the person who utilize this model can directly see those keywords and can verify whether this is really looking at or analyze the images properly or not. Then we just apply this technique to another problems, which is the anomaly detection. I think you are very familiar with the problem itself. Anomaly detection is just the approach to identify rare events from the significant difference from the normal distributions. So we are particularly interested in the lymph node anomaly detection. So as you can see, lower right side, the normal lymph node tissue has very regular structure, but in the abnormal lymph node tissues, basically this metastatic or the cancerous tissues have a lot different look. So by training a model only on the normal tissues, can we detect the abnormal tissues? So the very first work we did was using the diffusion model. So we just trained a diffusion model using the normal images only. And the idea here is that if you just reconstruct the normal the input image, then since the model only knows the normal structures, normal distributions, the reconstructed image will be normal. Okay. So even though you give the abnormal images, the reconstructed images will look like normal. So there will be a difference between the original image and the reconstructed image. But if you just use a naive diffusion model, it does not work very well for some abnormal tissue images. So to further improve the quality of the reconstruction, so we basically did the same thing. So we give the image, input image, and then prepare the text keywords. So that's the keywords describing the normal tissue characteristics. And then we match these keywords with the input image and find the most relevant keywords, and then using them to generate what we call the weighted prompt. So this prompt works as a kind of prior information to the diffusion process. So this is like this prior information basically push harder to all the reconstruction process towards the normal distributions because we use the normal keyword campaign. So this is the result. We look at the slide in the middle, and the box area just the image reconstruction from our model. So the in is basically the normal image. So given normal image, the generated image, the reconstructed image looks like normal. All this is abnormal image. And we look at compare the original abnormal image, then the reconstructed image is a lot different. The one that we reconstructed is a lot look like normal. But the one in the middle is basically the naive diffusion models. They just they don't really look different because they're just almost the same as the input abnormal image. So using this, we're able to improve the normal detection performance quite a lot. But after we finished this work, we have realized that, hey, we do have other types of knowledge as well, which is the abnormal tissues. So we collected keywords that describe normal tissues, but we also know about the cancer tissues, right? What the cancerous tissues look like. So we can collect the keywords for the abnormal tissues, cancerous tissues. So we basically have two types of keywords that are basically one describing the normal tissues, the other describing the abnormal or the cancerous tissues. So we try to use them to further improve the normal detection performance. So this is the kind of the same technique. So given one image, input image, we brought the normal text pool and find the most relevant keywords and generate the representative embedding vector. We did the same thing with the abnormal text pool. So we find the most relevant abnormal keywords and use them to generate the second embedding vectors. Then what these this leads us? So this basically leads us two types of the embedding vectors. The one is basically presenting the relationship between normal image and normal keywords. That's basically what we want to learn, right? So it is when we say the normal distributions, that's the distribution that we want to learn. And what about the second embedding? Second embedding just basically represents the relationship between normal image and abnormal text keywords. What is that? What is the relationship between a normal image with abnormal text keywords? It is not clear what it really represents. But one thing for sure we know is that there has to be a difference from normal image to normal text keywords. So our original intention was to use the second embedding vectors to improve the representation of the first embedding vectors. So how we do that? Okay, so first we push them far away, and then we try to cluster each of them tightly, so that we have better representation for the normal distributions. But what it turns out with that is that once we given at the inference, if you give the normal image, then we can still generate two types of the embedding vectors. They are close to the centroid that we have computed from the training data sets. So the distance to these two centroids are very close to each other. And as we give the abnormal image, then we can also generate two embedding vectors, basically abnormal image to normal text keyword, abnormal image to abnormal text. Since the model has not seen the abnormal image at all, so they do not know what to do with that. So what turns out is that those two embedding vectors just stay away from the two centroids that we have computed. So by simply calculating the distance to the two centroids, we're able to measure how abnormal they are. So we use that as an anomaly score. Then we were able to outperform most of the all the computer models that we have compared. As you can see on the right side, as we map these scores on the whole side image, it is example almost the same as the grassroots maps that we have obtained from the pathologies. And since we're using these text keywords, we can also provide the matching keywords, like you can see on the lower left side, so that the pathologists can look at these and can verify whether this is a good, really abnormal or the normal tissues. So I have basically shown you our recent work on using the large-scale AI models or the foundation models. So we basically try to use these image-based visual foundation models and the language models together to further improve the performance of the pathology image analysis. And I think there's still a lot of things underexplored, and there's some more opportunities in the for the future. But in that process, we believe that the human knowledge still remains invaluable. It's not just the AI-driven knowledge, and human knowledge is still very important. That will serve as both foundation and complement to AI systems. Thank you all. This is all I have for today.
Fantastic. Thank you very much. That was a really brilliant talk. So does anyone have any questions for Jin Tae?
Yeah, I have a question. Yeah, thank you so much for your talk, firstly. Just a small question. So with vision language models,
Yeah.
then sometimes they hallucinate. Have you observed any hallucination in your?
Yeah, because
And how do you?
so like in this case, we show the matching keywords, right? They're not like always 100% correct, but mostly they are very relevant. I think the hallucination is less than the common the LLM approach, because what we mostly do is just we limit the text pools. The LLM basically you have huge vocabulary, right? But we limit it into or in an order of 100. So there's the chance of hallucination that's much smaller, but it's still we have the chances that we're providing the wrong matched keyword. That area needs to be improved.
So you said multimodality, like images and text here. Did you try integrating any other modality like clinical reports or radiology? Like that to see?
Not yet. That's basically the text and images that has been the major modalities we have not able to explore it further. But recently we just started to exploring the spatial transforming data sets. I think the same kind of project will be
Can I ask about the work on the video?
okay.
So have you used a pre-trained model, one of the lab models, and then fine-tune it
Sure.
on a series of images?
Yeah. So basically, we did not really develop the whole architecture because then, which means that you have to train everything from the scratch. So we just take advantage of the pre-trained models, basically alpha models, and then we prepare these video clips. We just generated thousands of the video clips. So we just train it on the existing models. So it's just not just the video data only, because you can basically treat it as a one single image, right? You can have a single image. So the model can train can handle the static image as well. So we just basically here the focus was how we utilize the first to develop to construct the data set, and the second is how we utilize it. So we're not just training, just using the video clips as it is. We just we have a stages of the training, so we just use them in different manners. And then one is like supervised, and they also the semi-supervised and so on.
I have another question about the video stuff.
Mhm.
So kind of once you made this model, like how have you been using it, or how do you envision it being used?
So that was our the biggest criticism on this paper. So this still just is under review. So that's for that problem. So people saying like, hey, what's the usage of that? You don't have it, right? So this is, I think this is the way we want to move forward as then would like to have a model that can automatically just navigate through the slide. But that practice has not been done. So mostly it is through the reinforcement learning approaches, so that you have another agent that can navigate through the slide, and then based upon those navigations, and then you can have the descriptions at the end. So that's our final goal. But it's just that we did this because we just first want to see that is that really helpful to do any diagnostic tasks.
So you maybe train on some data on how pathologists navigate through a slide,
Yeah.
and then kind of play using the model
Right.
through the slide, looking at
Yeah.
it like that, and then see what diagnosis comes out.
Sure. Yeah.
We've also got a question from Afsan online, who was wondering if the WOI would be taken from pathology report directly. It's multimodal combining image and its descriptions, right? So the I can't remember what is word of. Do you see the question on the chat just there? It was wondering if the WOI would be taken.
No, it's just a WOI. It's just basically provided from the pathologist. We just specifically ask them to prepare the pool for very specific tasks like cancer grading or the normal detection. We just specifically ask for the lymph node normal distribution and normal characteristics and abnormal characteristics.
Sure. Thank you. And I suppose I've also got a question. So I know in the past you'll have some quite a lot of work in domain generalization. And of course, it's not been mentioned today, but is there, with the sort of the use of foundation models and multimodal getting text involved, is domain generalization just always a problem? Is it not a big problem anymore?
No, it is. It's kind of I would say that we kind of pretend that it does not exist. So, because that's kind of the whole different story, right? So it's just it be just because for example, like this video work, then don't really have other data sets to test on. So that's all I have, what we have. So for kind of domain generalization problems, then we need to kind of explore the another problems basically. So it is a huge issue, of course, but when we do these, and we're not really taking that problems. But unless the normal detection, I think I just forgot to mention here is that this one basically we tried two different data sets. So the model basically trained on the gastric data set, and then just we brought the exact same data set and tested on the communion, the breast data sets. So there's no further adaptations on the fine tuning at all, but still we're able to detect the abnormal tissues quite accurately, so over like 0.85 AUC, so which is a very high, but to our opinion. So we try to explore whether this can be able to apply to other types of the organs and the data sets from other sources. So,
Okay. Any other questions from anyone in the group or online? If not, then we'll bring the lunch in and we can draw the seminar to a close. But thank you very much, Jin Tae, for a really, really interesting talk. And we'll thank our speaker again.